Hey everyone, today we're going to talk about a superpower, and I mean a real one, the ability to see the invisible. We're going to explore how satellites can check on a forest's health, find hidden minerals, and even analyze tiny dust particles that change our weather, all by seeing colors that our own eyes just can't. So let's start with this idea of a planet's fingerprint. You know, every single thing on Earth's surface, every rock, every plant, every patch of soil, it reflects light in its own unique way. It's like a signature. But how in the world do scientists from space read these millions of tiny signatures to solve a much, much bigger puzzle?
I mean, really think about that for a second. From hundreds of miles up, our planet is just this beautiful wash of green, brown, and blue. So how do you tell the difference between a forest that's thriving and one that's quietly suffering from a drought? Or how do you pinpoint a specific mineral deposit we need for our phones and batteries?
Well, the answer is just so cool and elegant. It's not about seeing better with a bigger telescope. It's about seeing differently. We've built these incredible sensors that can see a whole rainbow of light, far beyond what our eyes were ever built to perceive. Okay, so let's pop open the hood on this spectral toolkit. We're going to look at the special sensors that capture these invisible colors and, more importantly, learn how to decode the unique signatures they show us. At the heart of all this is one concept: spectral resolution. Basically, like we said, everything has its own light fingerprint. A sensor with high spectral resolution is like a master detective. It can see tons of very narrow, specific slices of light, which lets it read those fingerprints with amazing precision. And you know, this is really where the magic happens, in the light we can't see. In the near-infrared, or NIR, healthy plants literally glow. And in the shortwave infrared, SWIR, the ground itself just comes alive, with different minerals and soil types practically shouting out their unique signatures. This is where the planet's real story is being written. Now, to capture this story, scientists basically use two main types of sensors. You can think of them as two different ways of reading that planetary fingerprint. First up, you've got your multispectral sensors. These are the reliable workhorses of remote sensing. They don't try to capture everything. Instead, they focus on a few really important, strategically chosen bands of light. Sentinel-2, for instance, has these special red edge bands that are just perfect for keeping an eye on crop health. They're all about efficiency and getting the job done. But then you've got hyperspectral, and this is where things get really, really wild. If multispectral is like taking a few key snapshots of a scene, hyperspectral is like shooting the whole thing in full high-def video. It captures hundreds of narrow, continuous bands, giving you the entire unbroken spectral fingerprint of whatever it's looking at. And that's the absolute key. Hyperspectral sensors don't just see green. They see that complete curve, the whole signature. A fantastic example of this is NASA's E-MITE mission, which is up on the International Space Station. It uses this exact tech to map the mineral makeup of desert dust to help us figure out how those tiny particles actually heat or cool our planet as they blow around the globe. But here's the twist. Having hundreds of bands of data, this incredibly detailed video of light, it actually creates a surprising new problem. Turns out, more isn't always better. I know it sounds completely backwards, right? You'd think more detail is always what you want, but in the world of data analysis, that's just not always the case. Yeah, it's a paradox known in the field as the Hughes phenomenon. After a certain point, adding more and more spectral bands can actually start to confuse the computer models. It can make them less accurate, not more, unless you have just an impossibly huge library of examples to train them on. This whole problem is called the curse of dimensionality. See, a lot of those hundreds of bands are kind of redundant. They're telling you pretty much the same thing. The real art is finding the true signal in all that noise. So scientists use these really clever techniques like principal component analysis, or PCA, to basically distill all that data down, finding the 5 or 10 master bands that hold the most important information. So if we can't just throw all 400 bands at the problem at once, how do we actually unlock all that hidden data? Well, the solution is surprisingly simple: a little bit of math and some clever visualization. Yeah, instead of trying to make sense of hundreds of bands all at once, we can combine just a few key ones into a single powerful number. It's called an index. And this is how we translate that super complex spectral data into a clear, straightforward insight. And the most famous of all of these is NDVI, the Normalized Difference Vegetation Index.
By just subtracting the red light from the near-infrared and then dividing by their sum, you get one single number that is unbelievably good at measuring plant health and how much of it there is. It's the absolute gold standard for monitoring farms and forests all over the world. And here's another incredible example, the normalized burn ratio, or NBR. It uses near-infrared and shortwave infrared to clearly map out how badly a forest fire burned. This is what emergency responders use to assess damage and plan recovery right after a fire. It's just simple math, but with a life-saving impact.
Okay, so we've got these really powerful numbers. That's great. But a map just full of numbers isn't very helpful, right? So how do we turn all this data into an image that our brains can actually understand in a split second? The answer is this awesome trick called a false color composite. Here's how it works. So our screens can only show red, green, and blue, right? So first, the satellite captures data in an invisible band, like near-infrared. Then, in step 2, we tell the computer to show that invisible NIR data through the red color channel on our screen. And the result is magic. Healthy vegetation, which is glowing in that NIR band, now shows up on our map as bright, vivid red. We are literally making the invisible visible. So finally, this amazing technology comes with one big, fundamental trade-off that every satellite engineer has to deal with. It's the obvious question, isn't it? If we have this incredible hyperspectral technology, why don't we just put it on a satellite that can also see things the size of a shoebox? You know, why can't we have both perfect color detail and perfect sharpness at the exact same time? Well, the reason is a fundamental compromise in physics, and it all comes down to collecting light. So think of a sensor's pixel like a bucket in the rain. To capture hundreds of very specific narrow bands of light, that's high spectral resolution, it's like you're trying to catch only the blue raindrops. Since there aren't many of them, you need a really wide bucket, a large pixel, to collect enough to get a good measurement. On the flip side, to get a super sharp image with tiny little pixels, that's high spatial resolution, that's like using lots of tiny buckets. To fill them up fast, you have to collect all the rain, not just the blue drops. So you have to choose. Do you want incredible color detail or do you want incredible sharpness? You can't have both. You know, at the end of the day, it's an incredible power. For the first time in human history, we have the tools to read our planet's vital signs in this exquisite detail. We can monitor our food supply, track climate change, and find hidden resources. We've basically been given a brand new way to see the world. So the only question left is, what are we going to do with what we see?